Good day, I'm Dr. T and welcome to my office. So today let's talk about halocarbons. So when we talk about organic compounds, we're typically talking about hydrocarbons. These are going to be molecules that are made of carbon and hydrogen. Sometimes the term hydrocarbon will also include those compounds that contain oxygen as well. It just depends on the context in which it's used. But strictly speaking, we're talking alkanes, alkenes, and alkynes. Halocarbons are going to start out life, or are going to look very much like an alkane, alkene, or alkyne. But one of the hydrogens is removed, and it is replaced with a halogen. That's going to be fluorine, bromine, chlorine, or iodine. Now, with this, you get a couple of interesting features. For starters, this is going to increase their density considerably. These atoms have a noticeably higher atomic weight than that of carbon, and as such, resulting compounds will be noticeably denser. So if you are separating a hydrocarbon from water, doing a liquid-liquid extraction per se, the hydrocarbon will float on top of the water. However, if you're using a halocarbon, it will sink and will be on the bottom layer. So if you're using a separatory funnel, a pear-shaped flask that helps with liquid-liquid extractions because it's got a spigot on the bottom, thus you can drain off the bottom layer easily. It's helpful to keep track of which layers on which, top or bottom. Now, the other couple of properties for halocarbons, these typically are going to create an interesting site for chemical reactivity, although depending on the reactivity, they might either be very reactive and facilitate the reaction, or relatively non-reactive. Halocarbons typically don't burn well. They interfere with the combustion process, and many of your fire retardants and firefighting approaches do involve halocarbons. That, however, is not necessarily a net benefit because they are also fairly rare in nature, and as such, most living systems do not have the appropriate machinery to deal with them, and thus they are typically toxic to varying degrees, and they are typically very poorly biodegraded. A lot of your insecticides are going to be these, and of course the classic DDT is a halocarbon. Effective insecticide, unfortunately, very low biodegradability, so it persists in the environment for a long period of time. Additionally, as I mentioned, these don't burn well, and typically the way we dispose of hydrocarbons that we don't want anymore is to burn them. Well, when halocarbons burn, they typically form compounds known as dioxins, which are notoriously toxic. Notice this whole toxic thing coming around? Yeah, halocarbons are wonderful to work with. They're potentially very, very useful, but disposing of the things ends up becoming quite an issue. So these are a class of compounds that, in the move to a more sustainable form of chemistry, known as green chemistry, we are trying to mitigate their use. Use less of them, replace them, and ideally not use as much or any when possible. That said, they are particularly useful compounds, so it's unlikely that they will completely go away anytime soon, but drastic reductions in the quantity of their use is a standing goal of the chemical community. So with that said, have a wonderful day, and I will see you in later videos.